So we have covered, earlier some hazards. We mentioned that we have structure hazards, data hazards, and control hazards. Extensively, we have seen the structure hazards and the data hazards. We will continue also with other examples of data hazards, and also we will cover in details the control hazards. But just like to refresh your information, to remind you about the first two, with the structure hazards, meaning that there is a structure problem. Suppose that two classes or two courses, they have or they would like to access this particular room at the exactly same time. This is a structure problem because both of us would like to access the same structure at the same time. Of course, we will not be able to have like a class with one instructor that will explain something and another class with another instructor to explain another things in the same place at the same time. This is impossible. So that's what we call the structure hazard. How we will solve that is just separate that, either to build like a wall in between or like try to find another place for the other class and so on and so forth. And this is what we have also mentioned with the memory. This is usually happen with the memory. If I would like to access the data memory and the instruction memory at the exact same time, and this is an issue, so the solution, of course, separate the data memory from the instruction. Data hazards, meaning that basically I need to use an information that is not available already yet in my pipeline stages. For instance, I would like to add whatever in one register with another register and put the results in a third register, a destination register. But one of these registers that I would like to add, either the RS or the RT, unfortunately, they are not ready yet in my stages from the previous instruction. So the previous instruction, they have to update their destination register, and then I have to use it. So unfortunately, if I use it earlier, then it has been updated. So basically, I'm not getting the correct information. And because of that, an hazard will occur. And this is, in this situation, we refer to that as data hazard. We will see control hazards in details later on, but similar concepts that, again, we don't know exactly where I should go as my next instruction. So if we have a jump or a branch, this means that I have to go to another place in some situations, or I can just fetch the next instruction directly in other situations. Because of that, again, I might have an hazard, and this we refer to as a control hazard. We'll explain that in details. And because of that, of course, we need to be careful on when exactly we can take our data. We also mentioned earlier, suppose that I have this particular code. As we have mentioned, that this first line is just doing a load word from that particular location in the memory to a certain particular register, which we refer to as T1 here. The next instruction is not using the T1, but it's loading another data or another particular data in the memory to a register called T2. Interestingly, the following instruction, which is add, is using that register or the data that has been updated in that, or hopefully that has been updated in that registers, and the need to add it to the T1 and then put that in the T3. Unfortunately, because this is directly after that, and as we have shown earlier, the data hazard will occur, and then I have to stall. And if I have to stall, then I will add one stall here. The same occurred actually with this one also, so I can have also another stall here. But if I will do like a code scheduling, meaning that the order here will change a little bit, but we have to make sure that this order will not affect negatively any of the results. If we move a little bit this earlier here, so this is I have here, this has been used here or there. So now with this one, the data is already ready. I don't need to do stalls. This is already ready. The data is already ready. I don't have to do any stalls. If we count the number of cycles that is needed after 2 stalls, we'll get 13 cycles, and you can do it by yourself. If we do it without the stalls, it will have 11 cycles, which of course I am increasing the throughput. So I have a better performance. Of course, the stalls is not something that we would like actually to handle. We would like or hope to reduce it as much as we can, because the stalls will reduce the performance. But unfortunately, they are required to get correct results. In the software situation, compiler can actually make amendments to the code to avoid hazards. But if we are implementing all of this by ourselves to the FPGA, so actually we have to do that by ourselves. However, we will not go that deep to build something that will do automatically an arrangement of the code, but this is just for your reference. Here it just shows you data hazards in the ALU. Suppose that I would like to do a subtraction, and after that and so on and so forth. And this registers is basically updated by the addition of whatever in register 3 with whatever in register 1, and then be allocated in my destination register 2. The one direct instruction afterward is using that register 2. This one is also using that register 2, and so on and so forth. We need to see how we can be able to detect hazards, and also how we can resolve this, and how we can do forwarding, and when we can do forwarding. All of these things we need basically to know. So going to that same code that is here, try to look at this code a little bit step by step and in details. I have the very first one that I would like to subtract this from that, and then put the results in register number 2. We would like to know first when exactly the register 2 will be updated. In which cycle in my stage pipeline stage this would be updated. As you know, the very first stage is instruction fetch, and then decoding, and then execution, and then the memory, and then the write back. Write back means I would like to write back, or to write whatever I have here into that register. That's why here it is updated. So basically this register is updated here. So register number 2 is updated at this write back stage, which is clock cycle 5. So at clock cycle 5, I have my data ready that I can use. My register 2 already has been updated with the correct information, which is the subtraction of these two registers. Okay, so that's fine. Let's see the next instruction. The next instruction is AND register number 2, which is basically needs the information that is here, ANDed with register number 5, and then put the results in register number 12. Okay, so if this is the case, here I will fetch my instruction. Here I will decode my instruction, meaning I have to pass to my ALU whatever in register number 2 and whatever in register number 5, because this is the decoding. In the decoding, I already took the instruction and I would like to decode it. I know now where exactly is my registers, and I have to pass that to the ALU. So the ALU will be able to do the AND. Unfortunately, now I am passing register 2 at clock cycle 3, while the register 2 already needs to be updated later on at clock cycle 5. So that means if I took it at this particular time instance, I'm not getting the correct answer, or I'm not getting the correct data that's supposed to be in register number 2. So register number 2 that I'm passing here, this is false information. It's not correct. And accordingly, everything else inside or in my pipeline would be not correct. Let's see that guy also. The next instruction. Again, I'm using 2. Order with that. I will fetch and then decode. When I decode, I have to pass here register number 2, register number 6 to my ALU. But register number 2 is already updated here. I need to use it here. So of course, I'm passing a false information, and accordingly, all of the other data will not be correct. How about the next one? The next one, again, is using 2 and 2. So basically here I am passing 2 and 2. Interestingly, it has been updated in clock cycle 5, and I'm using also in clock cycle 5. The good thing that if it is available at clock cycle 5 and I'm using as clock cycle 5, I'm actually using the correct information. Why? Because in this, as we mentioned, if we have this as a clock cycle, we will write or update my register number 2 at the rising edge as an example, and then read at the falling edge. So I have updated here at the first half, and I will read it in the second half. So that means that actually, although I have updated the register at that particular cycle, I still can read the correct information because of that sense. My clock cycle might be like that. Again, it is the same things. I will write at this one and I will read at this one, meaning one of the edges I will write, another edge I will read, and so on. So that basically whatever I'm passing here is correct. So this is wrong, but this is correct in this case. Can we find a solution that would relax that? Because unfortunately, if I would like to get this correct, that means that I have actually to do no operation here, to do no operation here, and then stall everything. This will be shifted here. So I'm using just 2 stalls in my pipeline. However, there is another actually trick that we can use in order to alleviate that, or just like solve this issue. How? By using forwarding. Let's trace whatever we have earlier again here with another prospect. So again, I'm using register number 2. So basically, I'm passing register number 2 to that particular ALU. Okay, that's fine. Let's see here. When register number 2 is updated, register number 2 is updated here. But let's go step by step on this particular stage of my pipeline. Register number 1 with register number 3. So register number 1 with register number 3, and then subtract. So this is subtract. And then the results of the subtraction is here. These results is what will go later on and be written in register number 2, correct? So at this stage, the output of the ALU is holding the correct information. So why not use it? Why I have to wait all the way till the end until I use it while it is already available here? The correct result is available at this stage, the subtraction result. Okay, so that's fine. So this means that actually my data is available at this particular stage. Look at this guy. This guy need to pass whatever in register number 2 and whatever in register number 5 to my ALU. Interestingly, the output of my ALU is holding the correct information of register number 2, so why not to pass it to the input of the ALU or forward it to the input of the ALU? If I forward it to the input of the ALU, so the ALU here is getting the correct result that should have been updated later on in my pipeline stages at this particular stage, and then I will get the correct results moving forward. Correct? First, I have to ask myself how I would be able to detect that and what I should do. First, I have to check if my RS or my RT is equal to the RD in my previous instruction or not. Because if my first source or my second source is equal to the destination of the previous instruction, so this means that there will be a hazard, and then I would need to forward. And as I have proven here, we need to forward from the output of the ALU to the input of the ALU. So that means I am checking if RS or RT is equal to the RD in the previous instruction or not. Meaning, I am checking whatever I have here as an RS and RT, and whatever here as I have as an RD, and if they are equal, then I can basically forward from the output of the ALU to the input of the ALU. But there is an important thing that I have to highlight. Before I will highlight here, I would like to remind you with the example that we mentioned at the very beginning, which contain the washing machine and dryer and folding and all of this kind of stuff. If you recall, we have a washing machine and then a dryer and then fold and all of this kind of stages, correct? With all the persons that basically are using these stages, did we use only one of each or did we replicate them? We just use one of each, correct? The idea, we have only one dryer, one washing machine, one dryer, one place to fold and so on, correct? And the idea with the pipelining is just moving from a person in a one stage to another stage, meaning that as soon as I finish the washing machine, I will move the very first person stuff from the washing to the dryer, and then the next person will use the washing machine. And so on. If that person, first one, finished the dryer, we're moving to the next stage, and that next person will move to the dryer, and the new person will move to the washing machine, and so on, correct? But now I have only one washing, one dryer, one folding, and so on, correct? Just one. Here is exactly the same. All of these are just one. One instruction fetch, decoding stage, execution, memory, and then back to the write back. This is exactly that, is exactly that, exactly that, exactly that. The only difference, I'm just taking camera shots or snapshots, yes, in terms of time. And I'm showing you in terms of time or clock cycles. However, they are exactly the same, meaning that this ALU is the same exactly as this ALU, is the same exactly as this ALU, and so on. So if I'm telling you going from the output of the ALU to the input of the ALU, in particular, in the implementation, as I will show you a little bit later today, that it is basically connecting the output of the ALU to the input of the ALU, to the same ALU. Here I'm just showing you in time. When you will do that, this is what we will understand when we can do it. This is basically the next one. Yes, so it is output of the ALU to the input of the ALU. With the same exact concepts, let's try to see that particular instruction. That particular instruction is using the 2 and the register 6. So basically at this place, I need to pass register 2, and this place I need to pass register 6. As we mentioned, register number 2 information is already here. In the next stage, it will appear here. So register number 2 is here before it is written there. So register number 2 information is here. And I need that information to the input of the ALU. So why not to take it directly from the output to the memory to the input of the ALU by forwarding? And if I do that, again, this information will be correct, and any information in the subsequent stages or clock cycle in the same pipeline will be correct. And I will get the same exact information as I would have done the stall and just wait. So why to wait in this case, since I can do forwarding? But again, the same concept, I'm checking if my RS or RT, meaning if this was 2 or this 2, any of these, if my RT or RS is equal to the RD in the one earlier previous instruction, then I have to do, there is a hazard and I have to do forwarding. But in this case, I will do forwarding from the output of the memory to the input of the ALU. So now I am not checking basically this to that. I am checking now the output of the memory, because this to that. Instead of this to that, I'm checking now this to that. If the RS RT here is equal to the RD, then there is a hazard and I have to do forwarding. But in this case, I have to do forwarding only from here to here. So again, I can forward from the output of the ALU to the input of the ALU because it is exactly the same ALU. Or I can forward from the output of the memory to the input of my ALU according to the examples that we have mentioned here. So here, let's see another example. We have a load word followed by a store word. Again, we need to think when the data here will be available and when exactly I need the data. And accordingly, I would basically decide if I will need to stall or not. And of course, we need to think about it if I have forwarding or I don't have forwarding. In this situation, assume that I have forwarding, and we need to know, do I have to stall between load word and store word or not? Think with the same exact scenario when this is available. So I would like to load a memory location to that particular register. Okay, so when I have that from the memory all the way to the register, meaning that register number 1 will be updated at that write back stage. But before it just updated to that write back stage, it is output from the memory the correct information that I need that's supposed to be in register number 1. So this information here is what I need. Correct? When I need that one, this is a store word from register number 1 to another particular data memory location. Correct? In my stages here, I would like again to write in my memory whatever has been updated in register 1. But register 1 has been updated here at this output of my data memory. So if I forward from the output of the memory to the input of the memory, I would get exactly the correct information in this case. And because of that, with the forwarding, I don't have to do any stall in this particular situation. And I will get the correct information in this situation without doing any stall. So here is just saying exactly whatever we have mentioned, how to detect the hazard. If my RS or my RT in that particular register, ID/EX or ID/EX, either the RS or RT is equal to the RD in register execution / memory, then I have to do forward, and this will be forwarding from the output of the ALU, basically, in this case, which is exactly the same scenario that we mentioned here. If this RS and RT is equal to that RD, then I need to forward from here. What is that? Each of these is just called as a matter between the connection of the previous stage and the next stage. For instance, this is ID stage and this is execution stage. So that one will be called ID/EX. That is just ID/EX. This guy is between the execution and the memory. So that guy will be called execution/memory. So I'm checking if my RS or RT here is equal to the RD here or not. If this is equal, then please do that. Remember, this EX, M, RS, and RT, IDX, RD. And this is what we have here. It's actually the other way around. IDIX, RS, and IDRX, RT is equal to that RD. I just flipped that. Sorry about that. Because actually, this one, this register should be here. This one is coming next. So it's actually in the previous register. So I just flipped it here. Sorry about that. Yes, because this is first. So this is actually going first and this is going next. So this is here will have the RD and this is here will have the RS and the RT. Sorry about that. With the same concept, I will check also the RS and RT in this particular same register with the RD in the memory write back register. So I'm checking again, whatever I have. Instead of this and this, I'm checking whatever in this and that. And again, if if RD here and then RS and RT here, because that actually belong to this and that actually belong to that in this particular situation. If this is the case, if they are equal, please forward from the output of the memory. What is the output of the memory? Which is this one. It is between the memory and the write back basically stage. So basically here you will forward from the memory and write back register, which is the output of the memory in this particular situation. Look at these Guys, here again, I'm doing the same thing, assuming that I would like to write register number 2 and here read register number 2. So I'm checking if this is equal to that or not. So I'm checking the output register of the out with the ALU with the input of the ALU. If this is the case, or if RT is the same, then there is a problem, there is a hazard, and of course I need to forward the data from the output to the ALU to the input of the ALU. Also, I need to check between this one and that one. If the RD here is equal to the RS or RT here, then again, I need to forward, but in this case, I will forward directly from the memory instead in this particular situation. Also, we would like to highlight that only I will need to do the forwarding if my register RD basically is not equal to 0. Only in this case, and also I have the register write as an example enabled in this particular scenario. And most important thing that RD is not equal to 0. Let's try to see like how we would be able to implement that, how we will be able to implement the forwarding unit in this particular scenario. So again, as we mentioned, this is my ALU. And the ALU, as we have indicated here, the ALU, this ALU, or any ALU, it's the same ALU, can get input from the output of the ALU, or it can get input from the output of the memory, or it can get input from just the previous stage. There are 3 scenarios here. And according to all of these situations, I need to see if I have to get the input from here, or the input from here, or the input from here. And this is exactly what we have in this hardware. This is my 2 inputs. These inputs to the ALU can come directly from the previous stage. This is one situation. Or it can come directly as an output of the ALU, which is here inside that. Or it can come as an output of my memory, which is basically here. Let's trace that here. So as an input to the ALU. So either from the previous stage, or from the memory, or from the ALU, correct? Since this is a multiplexer and multiple inputs, one output, I need to, of course, to have a selector. That selector will either choose this as an input, or that as an input, or that as an input. For instance, I can easily think that this will be 0, 0, this will be 0, 1, and this will be 1, 0. And this, for my forwarding unit, will detect the output of my EX/memory register and the output of my, memory/write back registers to the RS and RT of my ID/EX. So here I'm checking the RD with the RS and RT. If they are, each of them are equal, then I will decide which one I will pass. If the RD of this is equal to either the RS or RT of that, of course, I need to forward from the output of the ALU to the input of the ALU, meaning I need to pass that one. What is the code for that one, or what will be my selector in that situation? It will be 1, 0, because this is 0, 0, this is 0, 1, this is 1, 0. So my selector will be 1, 0. That means that I will pass that to my input to the ALU. The same scenario, that if the RD of this memory stage, memory/write back, RD is equal either to the RS or RT, so that means I will choose basically the one that is forwarded from the memory as an input. And since this is 0, 0, this is 0, 1, so my choice here will be 0, 1, which means I'm passing that particular to the that particular input to the ALU, as we can see from here. Whatever applied to the very first multiplexer as a selector forward A is applied exactly to the other multiplexer with a selector forward B. And then by doing this scenario, then I should be easily choose exactly where to forward from to my ALU. So again, according to whatever I have explained here, if this register RD is not equal to 0 and I have a register right, if this RS is equal to RD, and this is of course always in the ID IEX stages, is equal to the RD in the EX/memory, please choose the selector as a 1-0 as we have explained in the previous slide. If it is equal to the RT, also the same, choose 1-0. But if it is equal to the memory write back, which means I'm comparing the output of the memory to the input of the ALU. So this means in that case, I choose the output of the memory, which is the forwarding from the memory, and in this case, it is 0-1 instead, as we have explained here. This is 0-0, this is 0-1, and this is 1-0 in that particular scenario. So with the data path, with the forwarding, in this case, just applying the forwarding mechanism here, as you can see. And then, of course, with each of these stages, I have to pass whatever is needed to the next stage. So whatever is write back will be going all the way until the write back. Whatever in the memory will be went to the memory, and whatever I have here in the execution will just stay in the execution. And this is basically my forwarding implementation in this particular scenario. So this load word would like actually to load the word from this particular location to that particular register. These particular registers, of course, it will be appear at the write back here. However, as we mentioned, as soon as I will have the output of the memory, I know exactly that this hold also the register number 1. With the next instruction, assuming that I need a subtract, if I would like actually to forward, so this means that I need the correct data to the ALU here. Unfortunately, it is only available at this stage, so I can't go back on time, and because of that, I just need to stall, and all of these will be bubbles with whatever we call the NOP, which is no operation in this case, and I won't be able to do anything. However, if I do that, now the register number 1 is the input to the ALU. It is available at, as we mentioned here, at the output of the memory. Then I can easily forward it. Also in this situation, if my clock is here, so I would update it or write it in the rising edge, and then I will reading that in the falling edge, so I can do that actually in the same clock cycle, and it would appear also in this particular situation in the same exact cycle. So this situation, in addition to the forwarding here, you can have also a hazard detection unit that will take also the memory read in the ID/EX, and it would also take whatever I have from the ID/EX register in this particular case. So I can check also all of these RD and RT and put this as a input to the hazard detection, and it will choose also if I do a program counter right and stuff like that. It will also can choose exactly here if I will pass, as an example, whatever the data is, or I will just pass zeros or just bubbles or nothing. It's just like flush or all of these kind of things and so on and so forth. So now we have finished or semi-finished like the data hazards. Let's try to switch the gear to another hazard which is called control hazards. So what is control hazard? Usually, as we have seen so far in all the hazards, I'm going from one instruction to the directly one following it. So I'm going from the program counter to program counter +4. So I'm just moving from one instruction to the next one directly, correct? But this is not always the case in all of my instructions, in all of my situations. In some of my situations, I have jump instruction, for instance. And if I have a jump instruction, my next instruction is not in an address program counter +4. It will be in a certain particular address that will be written after the jump. I'm telling you, jump to that particular line. I am in line 2, but then you have to jump to line 1000, for instance. So the next instruction will not be the one in line 3, correct? The question is, when exactly in my stage I will know that I have to go to line 1000? We have to ask ourselves that things. So how much stalls or how much cycles I need to wait until I know that I have to go to line 1000? This is in the case of the jump, for instance. In the case of the branch, it is something similar, but with another scenario. For instance, I'm giving you branch something, comma something, and then go to a certain particular place, branch equal. That means that you need to check first if that register, the data in that register is equal to the data of the following register in the branch instruction or not. If they are equal, then you will go to the label address. Suppose that I have here branch equal register number 1, register number 2, and then here I'm telling you to a certain particular address. Let's say any address. If this equal to that, if this is satisfied, if I will take that, if this is correct, then I will go to that particular address. If it is not equal, what I will do? My next instruction in my sequence will be actually the program counter +4, the one next, directly next to that, correct? But I don't know exactly if I will take this instruction or if I will take the instruction in that particular address. I don't know in advance. I have to wait in my stages in the pipeline. At a certain point, I will understand or I will know this particular answer to my question. Are they equal or not? It might not be branch equal. It might be branch not equal. It might be branch less than or equal or greater than, whatever the thing is. That means that I have to wait a little bit in my clock cycle stages in order to get such an information. And this is what we call control hazards. Let's take an example. With the jump instruction, I have a jump and then a certain address here. What I will do first, that to fetch the instruction. Then in this case, I will decode. When I will decode, I will understand exactly what is that address. And after this stage, I know now where to go. Let's say like line 1000, for instance. So I know now that I will go to line 1000. Okay, that's fine. However, if I am going to get the next instruction to be fetched, I will fetch it here, the next instruction. But unfortunately, I already knew after this stage that I need to go to 1000 instead of just the next instruction. Because I might tell you jump, but jump to just the next instruction, or I might tell you jump to a huge, far away from me. But that means that I have to wait for at least one stall in order to know exactly where to go. Here, at this particular situation, I know exactly where to go. Then I can fetch the correct instruction, the target instruction in this particular case. Also, the same situation appears in the branch. If I have here a branch, if this is equal to that or not, please go here. If they are not equal, please take the next instruction to be executed. Unfortunately, this will take some time. At a certain stage, I will know if this is correct or not. We need to ask ourselves in which stage, and according to which stage, how many stalls do I need to do in this particular situation. So first of all, we need to know when I will know exactly the answer to the branch. According to this pipeline structure hardware implementation, the branch is available here, and I will know exactly at this stage, or maybe like after this stage or this stage, that the branch, what are the results of the branch. If I will take just the following instruction directly, or if I will go to the target instruction in this particular case. But at this stage, what is that stage? This is the memory. So let's go and see like how many stalls do I need in this case. We mentioned that we will know in the memory state the branch is correct or not. With the load word, so I need to fetch the instruction here. Unfortunately, I am still here. I don't know what to fetch. Correct? If I fetch that next instruction directly, I'm not fetching the correct instruction. It might be correct, it might not be correct, depending on the results here. If they are equal, assuming that this is branch equal, if they are equal, then I will go to the label here. It's like register 1, register 2, and then certain address. So if they are equal, I'm going to that address, which is not the following instruction. So if I will fetch the next instruction, it's not correct. Yes? So how many stalls do I need to do in this case? Let's check this example. Here it's telling you that branch equal 1, 3, and then go to a certain address. As we mentioned, it will be available here. So after this stage, I know exactly what to fetch. After this stage, from here forward, I know exactly what to fetch. If I know afterwards, so this means that if I fetch that instruction here at this particular situation, of course, this is wrong. If I fetch here, I can't go back. This is wrong. If it is available after that and forward. If it is available here, if I fetch here, it is again wrong. So that means only after this clock cycle, I can fetch correctly the instruction, and I will know exactly the correct answer if it is equal or not. So that means that I have to stall 1, 2, 3. So that means that if this stage is in address 40, the program counter plus 4 is 44. Yes? If this is taken, my next address or the taken address is actually will be to another address and that I have to take, but I have to stall 3. Also, if it is not equal, for instance, this guy and this has to be actually pushed down so I can take it at that particular or fetch it at that particular clock cycle, or if you think of pipeline stage, if you will, in this case. So that means because of this that I have to flush this instruction, unfortunately, until I know exactly what to fetch. So here in this particular slide, there is like a tiny error with this particular address. Assume that this 72 is correct, and this is basically the address that if the branch is taken, I'm going to that address. So that address should be actually, instead of 28, should be 7. Because what I need to do is 7 multiplied by 4, plus not this one, plus the program counter plus 4, plus 44. This is what's supposed to be equal to 72. That's why in some cases you might think about it like 8 multiplied by 32, since you didn't actually add it to the program counter plus 4 instead of you added to program counter instead of the program counter plus 4. But this has to be 7 in this particular case. So again, since as we mentioned with the branch equal, that actually we have to flush, and only with this particular clock cycle, I will be able to fetch the correct instruction. And if I will be able to fetch the correct instruction here, then that would be the correct situation. I either go to the branch equal target, or I can just go to the next instruction to be executed. As you can see from here, 3 stalls, fortunately, are a lot. That means that I am losing a huge amount of my performance. My throughput would be decreased a lot as soon as I have a branch instruction, which will give you an indication that in your code you have to avoid branches as much as you can, which of course is not the case. You will have multiple branches in your code since you need to do like this kind of either equalization or checking or stuff like that. How we can think of a solution? How we can solve such a problem? How we can decrease the amount of stalls? How we can, what we say, like reduce the branch delay in this particular situation? We need to think about that, and we'll share with you one of the solutions in today's explanations. As I mentioned, this is supposed to be 7 instead of 28, and then with 7, I'm targeting correct the 72. The idea that came out that instead of having the output or the correct results of the branch at this stage, let's try to add a small comparator in that stage. And if I add a small comparator here, with this comparator, the output, it will tell you if it is equal or not. So now I know my results a lot earlier in my stages, in my clock cycle stages, correct? I know it a lot earlier. And if I knew it a lot earlier, so this means that I don't have to wait that much till the very end until I know which instruction I should fetch. Because if I have a branch, I either will fetch the next instruction directly or the branch instruction, correct? Now, if I have the results here, which is a very nice idea, then I don't have to wait that much. Of course, what I'm paying is a little bit of more component, but this is a comparator. It shouldn't be that much complicated as I have here, like a very complicated, design with an ALU. I'm just only, in this particular situation or scenario, I'm only using a comparator. That's all. So if this is the case, how much we need to wait? If this is the case, my results will appear directly after this stage. After this stage, meaning that I can't, unfortunately, fetch the instruction here, so this has to be flushed. But anything after that can be fetched correctly. That means that I have to only flush one time instead of 3 times. So this would be enhanced a lot. We'll explain other ideas later on, but this is one of the ideas to be implemented in this particular case. So here with this example, assume that the branch is taken. So here with this code, assume that the branch is taken, meaning that the next instruction to be executed is this one. But with this idea, I'm telling you that you have to flush one. So if I'm asking you, I'm telling you that the branch is here, what would be the next instruction? The next one, of course, in this stage will be bubbles, no operation. I need to flush, correct? I'm not using anything, because if I will fetch here, I will not fetch the correct instruction. But I know if it is taken, that means I will go to the load word, and the load word will be my next instruction to be fetched. If you look here, if the branch is taken, my next instruction will be that one, which is basically that one, as you can see from here. So if the branch is taken, I have to flush for 1 clock cycle or stall for 1 clock cycle, and then the next clock cycle I'm taking or fetching the correct instruction or what we call the branch instruction, because this is branch taken. Branch taken means that the branch equality, if it is branch equal, is correct. If it is not equal, again, it is correct. It's just taken, meaning that whatever I would like to compare is correct. And if it is correct, meaning that I am going to the target branch address. And if I'm going to target branch address, this will be my target address in this particular situation.